So, in this lecture I will basically introduce power delivery system. So, what is the definition, formal definition of power delivery system? So, you can see this I have quoted from a book that which I kept in my reference. So, although this is not very standardized definition, but it gives the idea that what is power delivery system. Here power delivery system is basically also named as transmission and distribution system. Transmission and distribution system, it consists of thousands of transmission line and distribution lines. Okay. It also consists several other things like substations, transformers and several other equipment scattered over a wide geographical area. And as far as the transmission line is concerned, they are interconnected. As why if they are interconnected, already I mentioned in my last lecture. And the distribution networks are something different than the transmission network. Okay. But altogether they act as a unit to bring power from the generating station to the door of the customers. Okay. So, in order to understand this in detail, let me chalk out some idea about this power transmission and distribution system. Okay. So, here let me talk about some 4 important features. Number 1 is how power is transmitted from generating station or from generation to distribution. Then also I will talk about as I mentioned in my last lecture that from generation to distribution there exist multiple voltage levels. So, I will talk about different voltage levels. Which exist from generating station to towards the distribution. Okay. Then I will talk about topological or structural differences between transmission and distribution systems or transmission and distribution networks. And also I will talk about some brief idea about single line diagram, which we use to trace the power transmission and distribution networks, some idea about single line diagrams. So, this I will elaborate in my one of my modules of this course, but here I will give you a brief idea about single line diagram for tracing power transmission and distribution networks. So, these 4 aspects I will chalk out and give you a feel about this understanding this power transmission and distribution. Now, let me draw a block diagram, block representation to illustrate how power is transmitted and distributed from the generator side to the customer. Okay. So, first we will have generating station. Suppose this box is representing generating station. Okay. Now, one generating stations may have multiple number of generators, they are connected in parallel so that they can share load. Okay. And this I am talking about this particular generating station, I am talking about is the conventional type of generating station, like thermal power generating station. Typically in India, if you visit a conventional thermal generating station, you will see there exist 4 to 5 units. So, we basically represent them as 4 multiplied by 500 megawatt generating station. It means that we have 4 500 megawatt generation unit, or we have 4 number of 500 megawatt generators. Okay. Or we alternatively we can call it as we have 4 units of generating station, each having capacity of 500 megawatt. Okay. So, altogether this particular generating station, it is providing you 2000 megawatt of power. Now, after this generation, of course, this 2000 megawatt is not directly sent to the customers, because as a customers our requirement is not in that level. So, it undergoes several transformation, before it reach to the customer side. So, what exactly this transformation took place? After this generating station, we have transmission networks. Okay. What is the purpose of transmission networks? They are used to evacuate the power which is generated in the generating station, and they are responsible to bring this power to the area where customers live, where we have power demand. Okay. So, these transmission networks are essentially the carrier of power, and it is directly connected to the generating station and then brought power to the nearby area where people live. Now, next building block is of course our distribution system or distribution networks. Now, what is the purpose of these distribution networks? These distribution networks are basically responsible to distribute power to the customers. Okay. We have different types of customers and they have different requirement. So, these distribution networks take power from the transmission networks and distribute among the customers. This is simple philosophy. Now, we have hundreds of generating stations, therefore, we have several thousand circuit kilometer of transmission line, and we have very large number of distribution networks. They involve the overall power transmission and distribution. Okay. Now, the question is, do we bring power from this generating station to the distribution networks at the same voltage level? The answer is certainly no. So, that is why I said that there exist different voltage levels, those things I will be discussing. Okay. Now, generally this generation voltage level typically around 10 to 20 kV, kilovolt. kV stands for kilovolt. So, that means these generators, they generate that amount of power, 500 megawatt power each of this generator generate at a voltage level of 10 to 20 kilovolt. Okay. Now, this 10 to 20 kilovolt is not transmitted by the transmission network. Okay. So, we upgrade this voltage level, by this voltage level to the voltage level of the transmission networks. So, this upgradation took place in substation. So, what is that substation? In substation we have different number of transformers, and their purpose is to upgrade this voltage level from generation voltage level to the transmission level voltage. Okay. Now, what are the transmission level voltage we have in India? We have different transmission level voltage starting from 220 kilovolt, then 400 kilovolt and 765 kilovolt. Okay. So, these are the different transmission voltage levels. So, in the substation we have transformer, this sign is representing a transformer. There are multiple number of transformer as such, which are basically responsible to convert this voltage level to generation voltage level to transmission voltage level. Okay. Now, the question is why we need this transformation, why we need this transformation, why do not we generate whatever voltage, that voltage we should not transmit. So, there are some issues, okay. Particularly this power, if I represent it as capital P, it is proportional to voltage multiplied by current. Okay. Power is proportional to voltage multiplied by current. Now, if we transmit huge amount of power at lower voltage level, of course, the current flow through this transmission network could be higher. Whereas, if we go for higher and higher voltage level, this current which will flow through this transmission network will be less. The intention of transforming this generation voltage level to the transmission voltage level is to reduce the amount of current that should flow through the transmission line, Okay. Now, the question is why we need this reduction of this current. Now, there are two important aspects. One is the construction of transmission lines, they are made of transmission line conductors, okay. And this conductor size, the conductor cross section depends upon how much current you intend to flow through this particular transmission line. Okay. So, if you construct a transmission line which should carry higher amount of current, so you need to go for higher cross sectional size of the conductor, which will increase the cost and it creates even constructional complexities. So, this is one aspect that if we can reduce the amount of current, we need a conductor having a lower cross sectional size. Therefore, it constructional means tower and all these things would be less expensive. Okay. This is one issue. Another issue is that while transmitting power from generating station to the customers via this transmission and distribution networks, there exists a power loss, which is very important factor, and this power loss is proportional to the square of the current. It is basically I square R loss that we know. Okay. Now, if we can reduce the current, obviously this power loss will be reduced. Okay. So, this is the two important things that one should remember, for which we go for the change of this generation voltage level to a higher value transmission voltage level, or alternatively I can call that that is the reason why transmission voltage level is higher than the generation voltage level. Now, the question is, after this transmitting this power with this higher amount of voltage level, we need to again downgrade the voltage level. So, sometimes this transmission networks is directly connected to the distribution networks, or there exists again a intermediate block which we called as sub transmission line or sub transmission network, whose voltage level is little less than this transmission network voltage level. it is around 110 kV or 132 kV and so on. Okay. Now, this sub transmission network, they are basically of multiple numbers who brought this power to the nearby of the distribution networks. Now, again, so in that case, in order to have this sub transmission networks whose voltage level is less than the transmission network's voltage level. So, we need some voltage transformation, we need some transformer in between, or we need some substations to be installed beyond this transmission network or at the junction of the transmission networks and sub transmission network, where we will be having multiple number of transformers to convert the voltage level from the transmission line voltage level to the sub transmission line voltage level. Okay. And then this sub transmission network is connected to the distribution network, whose voltage level is normally around 11 kV or 33 kV in India. Mostly it is 11 kV distribution voltage level is used in India. Okay. So, in order to again this change this sub transmission line voltage level to the distribution network voltage level, we need to install another types of switching substation, who will be responsible for transforming this sub transmission voltage level to the distribution voltage level. Okay. So, this is how power flow from generating station to distribution network. So, there exist multiple number of components which include substation, which include transmission network, which include distribution network, which include several different types of substation. For example, this if you visit any thermal power plant in India, you will see inside the thermal power plant complex there exists a substation. This substation is basically for upgrading this voltage level from generation voltage level to the transmission line voltage level. Okay. But apart from that, there exist other types of substation, as I said, in between this distribution network to sub transmission network. This is to transform this sub transmission voltage level to the distribution network voltage level. Also, in between transmission network to sub transmission network, this is to transform the transmission line voltage level to the sub transmission line voltage level. So, you can see there are various voltage transformation took place in the process of power flow from generating station to the distribution networks. Okay. First upgradation of voltage level from generating voltage level to the transmission line voltage level, then downgradation of this voltage level from transmission and sub transmission voltage level to the distribution network voltage level. Okay. So, this should be understood as a power distribution engineers or researchers. Okay. So, these first two aspects already I discussed. Okay. Now, next two things that I should discuss before I show my slides to you. One is topological or structural difference between the transmission and distribution networks. Another is single line diagram. Okay. That means, basically there exist some differences between the transmission network structure and distribution network structure. That is the thing that one should understand. Okay. And also there is a practice to represent this transmission and distribution networks with a single phase equivalent circuital form. We call it as single line diagram. Sometimes we abbreviate it as SLD. So, these two things I will discuss before I show you my slides to you. So, first let us discuss single line diagram. What is single line diagram? So, as you know, I hope that most of you have some fair idea about this 3 phase electrical system. You know that as long as we consider the system is balanced, we can represent a 3-phase system in a single phase equivalent form. Okay. So, here the assumption is that we have a balanced system. Now, what do you mean by balanced system? Balanced system means we have a 3-phase voltage source which are having equal magnitude of this voltage and they are equal phase angle apart to each other. Similarly, we have identical 3 loads which carry equal amount of current and also these currents are exactly equal angle space to each other. Okay. So, both the voltage and current magnitudes in the individual phases are equal and they exactly are 120 degree apart to each other. Now, as long as this works, we can represent, we can simplify this 3-phase system in a single phase equivalent form and we usually represent this single line diagram like this. Suppose this is my generator, this is my generator. Then we have of course, this transformer, this is suppose the representation of the transformer and although they are of 3 phase, generator is of 3 phase generator, transformer is of 3 phase transformer, the line or cable which is connecting this generator to transformer, they are also of 3 phase, but we can represent them in equivalent single phase form and we keep a symbol like 3 parallel line to symbolize that although we are representing them in a by a single line, but they are actually of 3 phase. Okay. So, then we have this transmission line, okay. And then this transmission line is also 3 phase. Then we also have a some again transformer for sub transmission line which is also 3 phase, and then again we have some transformer and distribution line which are also 3 phase. Okay. This is the way of typical representation or typical single line diagram of a typical power system. Means this type of things you might have seen in your undergraduate level power system course. Okay. So, this is the representation of transmission line, this is the representation of your sub transmission line, and this is the representation of distribution line. And this nodal point or junction between this voltage level of this transmission line and this line, they are represented by this thick parallel lines. They are basically called as bus. So, of course, this bus is the nodal point of this generating station and the transmission line. This bus is the nodal point of the transmission line to sub transmission line. This bus is again the nodal point of the sub transmission line and the distribution lines. So, these are called bus, and many a times we also provide some nomenclature of those buses like bus 1, bus 2, bus 3, bus 4. So, these things probably you might have seen in your undergraduate power system course. Okay. So, this is the single line diagram and we follow this this is standardized single line diagram we follow worldwide to represent transmission and distribution networks. Okay. Now, as I said, what is the topological difference of a typical transmission line and a typical distribution line? So, in order to understand that, let me draw a typical single line diagram of a transmission network and a typical single line diagram of distribution network. Okay. So, suppose this is my typical representation of a transmission line. Okay. So, here if you look at this representation, single line diagram representation, this is suppose generator 1, this is suppose generator 2, this is suppose generator 3, which are located, which are spread in a vast geographical area, but they are connected through this transmission line. So, this is one transmission line, this is another transmission line, this is another transmission line, and this is another transmission line. Okay. We can represent this nodal point at the nomenclature of these buses. Suppose this is bus 1, this is bus 2, this is bus 3, and this is bus 4. Okay. So, we have here a 4 bus system, and we also have a 3 generators connected in 3 buses, and in one bus we do not have any generators, but this is connected to the sub transmission network to feed the load. Now, we have 4 transmission line. This is suppose line 1, which is connecting bus 1 to bus 2. This is suppose line 2, which is connecting bus 2 to bus 3. Let us name this one is line 3, which is basically connecting bus 3 to bus 4, and this is line 4. So, they are all transmission line. We represent them by a single line diagram, but they are of 3 page like this. So, if you want to represent this 3 page nomenclature, then you can provide this 3 parallel line, which will signify that they are of 3 page, but normally we do not keep this dotted line. We can simply write means as a power system engineers, we understand that they are of 3 page, but we are representing them in a single page equivalent form. This is the typical structure of a transmission line. Structure of topology of a transmission system. Okay. We have 4 number of buses, we have 4 number of lines. This is a typical system, but normally practical transmission network is of having multiple number of generators, hundreds of generators and hundreds of lines. Okay. And topology also changes. There may exist another line which is connecting bus 2 and bus 4 and so on. So, there might be different type of structure, but this is the general single line diagram to represent a transmission system. Okay. Now, what we can note down from this figure, that you can see that normally transmission networks is a type of mesh network. Okay. So, it creates loop and it creates meshes, whereas there is a difference of this network topology of the distribution networks. So, let us see how this distribution networks will look like. As I said, this distribution network will basically start beyond this sub transmission network, and they are connected to the load. And there are 2 types of distribution network. One is called primary distribution network, another is called secondary distribution network. This primary distribution network is normally of 11 kV, and the secondary distribution network in India is normally of 400 volt 3 phase. Okay. By the way, one thing I should tell that for those who do not have idea, that whatever these voltage levels I have shown in my last slide, that 10 to 20 kV, this 220 kV, 400 kV, 765, 11 kV, 33 kV, all are basically line to line voltage. So, many times this is not specified, but as a power system engineers you should know that they are line to line voltage, they are 3 phase voltage, and this is the voltage between 2 lines. Okay. Now, let us see that how a distribution network looks like. Okay. So, as you can see that distribution network is far away from the generator. So, So, distribution network is far away from the generators, and that is why normally under conventional conventional type of distribution system, there is no generating source. Conventional type I am talking about. Now, things are changing with time, those things I will discuss in my different modules, but a conventional distribution networks, they do not have any generating source connected. Okay. So, they are started with one feeding point, and that feeding point is the basically distribution substation. This distribution substation is connected with the subtransmission system, and a distribution network starts with this distribution substation. And this inside this distribution substation, we have different distribution transformers, which transforms the subtransmission voltage level to the distribution voltage level. Let us consider that 132 by 11 kV transformers. Okay. There might be multiple number of transformers, which are basically used to transform this voltage level and to distribute. Now, then how this distribution networks looks like? Then we have a long distribution lines, and these distribution lines are connected with different nodal points, connecting different nodal points. Each nodal points is having certain load connected to it. Each nodal point is having certain load connected to it. So, this is so on. So, each of having certain load. So, these loads you can consider as these are all loads. These loads you can consider as the residential complex or a small residential locality, or maybe a commercial complex, or maybe an industrial complex, and so on. Okay. So, basically distribution networks having a long feeder. These are all 3 phase. So, you can understand these lines are of 3 phase, but they are directly connected to the load. Okay. Now, this long distribution lines, which is basically connected to the distribution substation towards the load, they are basically also named as distribution feeder. Okay. This is a trunk feeder, and there might be some lateral feeder as well, like this particular node is connected to another load, for example, here, then this one is connected to another load. This particular nodal point is connected to another load, for example, here, then this is connected to another load. So, these are basically called lateral feeders. This is main feeder, this is main feeder or trunk feeder, and these are called lateral feeders. So, in a typical distribution network, we have multiple number of main feeders, and each main feeder is connected to a multiple number of lateral feeders. Okay. Now, sometimes in order to analyze this distribution network, we also rename this nodal point as 1, 2, 3, 4 and so on. So, we generally keep the substation as number 1 bus, and then next nodal point is bus 2 or node 2, next nodal point is bus 3, bus 4 and so on. So, this one has to understand. Now, if you look at this distribution network, so this is a typical structure of distribution systems. Now, if you look at this difference between this structure and this typical structure of transmission system, then one can understand that normally this transmission system is of mesh system having loops. And what is the purpose of this mesh system? This has some advantage. What is that advantage? The advantage is that because of this mesh structure, they are more reliable, reliability is higher. Whereas, this distribution network, they are basically of radial in structure, they are basically of radial in structure. Okay. What do you mean by radial? Radiality or radial structure means power flow is always unidirectional. Okay. Power flow is always unidirectional starting from this substation towards this load. Okay. So, power flow is always unidirectional, whereas in a transmission line power flow is bidirectional. Power can flow from bus 2 to bus 1 or vice versa. So, distribution networks intentionally kept as radial, so that power flow is unidirectional, and because of that this system is very simpler to operate. So, if power flow is the unidirectional, you can understand that suppose at any nodal point, what is the power that is flow from this point to that point, this point to that point, that is node 2 to node 3, you can easily determine by applying Kirchhoff's current law at this particular node. Okay. So, the power flow between this node 2 to node 3 would be simply equal to this, which is power flow summation of this power flow from node 3 to 4 and the power which is drawn by this particular load. So, if we apply KCL over here, so you can eventually find out what is the current or power that is flowing through this any particular line, but things is not as that simpler to for this type of mesh system. Okay. So, you can understand by looking at the difference of this topological or structural difference of these two systems. Okay. And because of this simplicity, the protection system design is and protection logics are much simpler for this radial system, and that is why in India or in other countries also distribution networks are purposefully kept as radial, even though they are not radial, but they are operated at radial. I will show you in later course of time. They are operated as radial, so that this will work with simple operational logic. Okay. So, with this let us see some other factors for power delivery system. First of all, you can see what are the goals of power delivery system. This goal is to cover utility service territory, reaching all the customers who wish to be connected. So, as a power distribution engineer, your goal would be to design a network such that all the customers under your geographical territory would get power from your network. Okay. So, this is one thing. Second thing is that they should have sufficient capability to meet the peak demand. Now, what is peak demand? Again, it is a technical term, I will discuss in my next lecture, but one should understand that the load is certain parameter which is changing with time. Sometimes load demand is very high, sometimes it will very less. So, whenever it is very high, your design network should have the capability to meet that particular demand. Then next thing is that provide satisfactory continuity of service. As in my introductory lecture I mentioned, as being a customer, we do not listen anything, but we do want that we should have uninterruptible power. In order to achieve this, you should have a very reliable network. Okay. So, in order to have a satisfactory continuity, you should have a very reliable network. So, these things you have to ensure. So, this is also one of the goals for power delivery system. Also we should provide stable voltage quality. What is voltage quality? All these things I will discuss in later course of time, but as a customer, for example, most of us customer of single phase customer. So, our rated voltage level is 230 volt single phase. So, whatever may happen to the network, but I wish to have this 230 volt available at my home. Okay. So, this one everybody should understand, okay. And that is basically called voltage quality, I will discuss, and also to maintain the power quality to the customer. So, there are many power quality issues, particularly with the inception of various types of sophisticated electronic devices by the customers, but they are very sensitive of this voltage. So, we should maintain this quality. Now, this I already discussed the historical development of transmission and distribution system. It was started in, as I mentioned in the last lecture, last 2 decades of 19th century, and slowly it started to flourish in different parts of the world in between 1900 1910 to 1950-60. Then there was a time that people were not much expectation, not much expectation. So, if there was any power interruption, they think that okay, this is natural, okay. But things was change after the inception of digital computers. So, they are very sensitive of this interruption. So, we do not wish to have any interruption in order to save those electronic devices. So, mindset of the consumers changed during that point of time. Okay. Now, by keeping all this in mind, we have this system restructuring in our country as well as in other countries. In India, it was happened after the implementation of Electricity Act 2003, and there after that lot many changes took place, and power business becomes more competitive, and there are more participation of various players. Okay. So, there are some thumb rule for power delivery system. Already I mentioned that what are the thumb rule? It is more economical to move power at the high voltage. Okay. So, this already I mentioned why we go for that. Second is utilization voltage is useless. What do you mean by utilization voltage? This utilization voltage is the voltage at which a device consume power. Okay. For us, it is all of the residential customers, we have these devices rated as 230 volt single phase. Okay. For a residential customer, our voltage level in our country is 230 volt single phase, that is the utilization voltage. Okay. And some of the industries, they have equipment which are rated of 400 volt 3 phase. So, for them this utilization voltage is 400 volt. So, normally you know this 400 volt 3 phase and 230 volt single phase, they are of utilization voltage in our country, and you can go back and see that these voltages are useless in the sense that we cannot transmit and distribute, or we can generate and distribute the customers with this utilization voltage. Okay. So, power must be delivered to the relatively small quantities at the lower voltage level, this is known to us. So, this is a typical power delivery system. Acknowledge this figure from this Lee Will's book. You can see that this is the generator, then we have this transmission network. These are basically typical representation of transmission line towers, and they are having you know transmission lines connected to it, transmission conductors connected to it. Then we have switching station or substation. This is substation where you downgrade this voltage level. So, this is the substation at which voltage is upgraded. This is the substation at which voltage is upgraded. This is the substation at which voltage is downgraded to the sub transmission line voltage level, and then further this is the substation where voltage is further downgraded to the distribution level voltage. Okay. So, this is the brief overview of a power delivery system. Then this is the distribution feeder which brings power to the customers, and this is the basically primary distribution feeder. In our country, it is of 11 kV. So, again we need to downgrade this voltage level by using distribution transformer. This is the distribution transformer to the utilization voltage level. This utilization voltage level, as you know, it is of 400 volt 3 phase or 230 volt single phase. Okay. So, next we go for this hierarchical system. So, you know this transmission system, it is used to evacuate power. Then we have it is the first hierarchical system which is near to the generating station. Then we have sub transmission system, which is basically the junctional point of this transmission system with the primary distribution system, and then we have primary distribution system and we have secondary distribution system. So, this is the hierarchical system already I discussed and I chalked out to illustrate you, and these are the typical voltage levels of this transmission, sub transmission, primary distribution and secondary distribution. As I mentioned these voltage levels of our country, but in other countries they have different voltage levels. For example, this we use 33 kV, they use 34.5 kV, we use 11 kV, they use 13.8 kV, but there exist hierarchical voltage level and power levels, those things you have to understand. So, of course, one thing you have to remember here is that this transmission system, its capacity is much higher, it can carry several megawatts of power. Sub transmission system, this is of multiple numbers, but its capacity is bit lower. Then primary distribution system, each capacity is much lower, only they can provide you 2 to 5 or maximum 10 megawatt of power, and then secondary distribution system capacity is further low. Okay. So, these are the generic features that one should know, that each level of power is fed power by the one above of it. For example, sub transmission level gets power from the transmission network, distribution networks gets power from the sub transmission network. Okay. Now, both the nominal voltage level and the average capacity of the equipment drops from level to level as one moves from generation to the customer. So, net capacity of each level increases as one moves towards the customer. For example, a power system might have 4500 MVA of substation capacity, but 6200 MVA of feeder capacity. It means that one feeder is not having 6200 MVA capacity, but there exists a huge number of feeders, and if you aggregate all this capacity, it would be much higher than the transmission capacity. Similarly, it should have 9000 MVA of service transformer. It does not mean that one transformer or two transformer rating is 9000 MVA, but it is if you aggregate the whole capacity, it will be something like that. Then also reliability drops. This thing I will discuss in due course of time. It means that distribution networks, they are suffer from more number of outages, and therefore, they are less reliable than the transmission networks. Why so? I will discuss. This is the difference of transmission and distribution networks. Already I discussed the topological difference, but balanced and unbalanced wise, transmission network is relatively balanced, distribution network is relatively unbalanced, but primary distribution networks often are balanced. Then lines are of transposed in transmission line transmission network, so that it can reduce the amount of voltage imbalance, but in distribution networks we do not have transposed line. Power losses is usually low in transmission network, because as you know, it is having higher voltage capacity, lower current. So, distribution network is high. Fault occurrence, whichever I mentioned in my last slide, is less in transmission network and high in distribution network. So, these are the utility transmission and distribution equipment. Already I mentioned about all of them, like transmission distribution lines, switching station, substation, service transformer. Then also we have some other equipment like reactive power compensator. Those things I will discuss in due course of time, and some other compensator we also have, we will discuss. So, next we have some generic features of transmission and distribution lines. They are made of electrical conductor, and mostly we use aluminum made conductor, and these lines can be either overhead conductors or underground cables, but except some metropolitan cities, they use the underground cables for distribution purpose only, but transmission lines are of all are of overhead lines or having overhead conductors, so as the distribution line also, because underground cables, they are basically costly equipment. Okay. So, overhead line are of economical, underground cables are more reliable, but they are costly. So, they are used in highly population density areas. This is the standard of a conductor, this is how it looks. We have these stranded conductors, this is the steel strands which is used for tensile strength of the conductor, and this is the how different strands, aluminum strands are used to flow this power. There are some specification by which we made we differentiate one type of conductor to the other conductors. Normally C mils is one of the definition. So, this is how we can convert C mils to diameter in inch. So, this already I discussed. This switching substation is another important, switching station and substation is another important thing for transmission and distribution of power. If you visit any substation, in fact, in our IIT Guwahati campus we also have a distribution substation. So, if you visit there, you will see there are many equipments, which include circuit breaker, which include different protection system, control, and there is a control room to monitor all these things. These are some of the things which will be required for planning of power transmission and distribution system. So, planning, there are two types of planning cost, one is called capital cost, another is operating cost. So, capital cost involves this installation and installation cost of the new equipment or for new reinforcement of the equipment. Operating cost is for operational cost wise, like it includes the cost of this maintenance, it also includes the cost of the power loss. Those things I will discuss. And this is the book which I have followed for preparing these slides. So, I sincerely acknowledge this book H. Lee Wills, Power Distribution Planning, to get various ideas of this lecture. Okay. Thank you.